Hello friends, in this video we will see the topic convergent sequences of real numbers. Let's see the definition of convergent sequence. A sequence xn of real numbers is said to be convergent is said to be convergent if there exists a real number L, if there exists a real number L such that L is a limit of the sequence of real numbers xn, n greater equal n naught. Note, if L is a limit of sequence of real number xn, then we can say that the sequence of real number xn converges to L. Let's see the examples of convergent sequences of real numbers. First, let xn is equal to 1 by n for all n belongs to a set of natural number n. Then the sequence xn is a sequence whose first term is 1, second 1 by 2, third 1 by 3, next 1 by 4, and so on. And we can observe that this sequence converges to a real number 0. Let xn is equal to n upon n plus 1 for all n belongs to n. Then xn is a sequence of real number whose first term is 1 by 2, second term 2 by 3, third term 3 by 4, fourth term 4 by 5, and so on. And this sequence of real number converges to 1. Let xn is equal to 1 plus 1 by n raised to n for all n belongs to n. Then xn is a sequence whose first term is 1 plus 1 raised to 1, that is 2. Second term is 1 plus 1 by 2 raised to 2. Third term is 1 plus 1 by 3 raised to 3. Fourth term is 1 plus 1 by 4 raised to 4, and so on. You can observe that this sequence of real number converges to a real number E. Let's see one theorem. Any convergent sequence of real numbers converges to a unique limit. Converges to a unique limit. Let's see the proof of this theorem. Let x and b any convergent sequence of real numbers suppose L1 and L2 are real numbers such that xn converges to limits L1 and L2. Then we claim that, see, in this theorem we have to prove that any convergent sequence of real numbers converges to a unique limit. And here we have assumed that L1 and L2 are real numbers such that xn converges to limits L1 and L2. So here our claim should be L1 and L2 are not distinct real numbers. Actually, they are equal. Consider mod of L1 minus L2. We can write it as L1 minus xn plus xn minus L2. Here we have subtracted xn and added xn to keep its value same. And see, this is true for any natural number. Means we have added xn and subtracted xn. We can write it as mod of L1 minus Xn plus Xn minus L2. See, by triangle inequality, the right hand side is less than or equal to mod of L1 minus Xn plus Xn minus L2. Means mod of L1 minus L2 is less equal by triangle inequality, right hand side is less equal mod of L1 minus Xn plus mod of Xn minus L2. So we will have mod of L1 minus L2 is less equal mod of L1 minus Xn plus mod of Xn minus L2 for all n belongs to n. But mod of L1 minus Xn is same as mod of minus of Xn minus L1 mod of minus of L1 minus Xn, and it is equal to mod of Xn minus L1, and it is also true for any natural number n. Therefore, we can write mod of L1 minus L2 is less equal mod of Xn minus L1 plus mod of Xn minus L2 for all n belongs to n. Call this as 1. Let epsilon greater than 0 be any given real number. We have sequence of real number Xn converges to L1. Therefore, for epsilon by 2, see, since epsilon is positive, epsilon by 2 is also a positive real number, and since Xn converges to L1, for epsilon by 2 greater than 0, there exists a natural number n1 such that mod of Xn minus L1 is less than epsilon by 2 for all n greater equal n1. Call this as 2. Similarly, we also have sequence of real number Xn converges to L2. Therefore, for epsilon by 2 greater than 0, there exists a natural number n2 such that mod of Xn minus L2 is less than epsilon by 2 for all n greater equal n2. call this as 3. Take n naught is equal to maximum of n1 and n2, then n naught is equal to n1 or n2. Since n1 and n2 are natural numbers, n naught is also a natural number. And since we are taking n naught is equal to maximum of n1 and n2, therefore n naught is greater or equal both n1 and n2. If n is any natural number greater or equal n naught, then n is greater or equal n1 as well as greater or equal n2. If n is greater or equal n naught, and already we have n naught is greater or equal n1, so n is greater or equal n1. Similarly, n naught is greater or equal n2 and n is greater or equal n naught, so n is greater or equal n2. But for n greater or equal n1, we have mod of xn minus L1 is less than epsilon by 2, and for n greater or equal n2, we have mod of xn minus L2 less than epsilon by 2 by 2 and 3. It implies addition of xn, addition of mod of xn minus L1 and mod of xn minus L2 is less than epsilon by 2 plus epsilon by 2. See, right hand side is less than epsilon. Epsilon by 2 plus epsilon by 2 is epsilon. But by 1, mod of L1 minus L2 less equal mod of xn minus L1 plus xn minus L2, we can write left hand side. We can see that left hand side is greater than or equal to mod of L1 minus L2. Therefore, we can write mod of L1 minus L2 is less than epsilon. That means we have mod of L1 minus L2 is less than epsilon for n greater equal n naught. But L1 and L2 are independent of n. So you can see that values of n1 and L2 are not depends on n. Therefore, L1 minus L2 is less than epsilon for any n. But We know that mod of any real number is always greater equal 0, but mod of L1 minus L2 is greater equal 0. Therefore, we can write 0 is less equal mod of L1 minus L2 is strictly less than epsilon. And we can say that this is true for any given epsilon greater than 0. Means here epsilon is arbitrary positive real number, but epsilon greater than 0 is, or you can say that, but epsilon is any positive, any arbitrary positive real number. Therefore, this is possible only if mod of L1 minus L2 is equal to 0. And mod of L1 minus L2 is equal to 0 is possible only if L1 minus L2 is 0. And therefore, L1 is equal to L2. And this was our claim. Means L1 and L2 real numbers such that xn converges to limits L1 and L2 is possible only if L1 equal to L2. L1 and L2 cannot be distinct, and hence any convergent sequence of real number converges to a unique limit. Let's see definition of divergent sequence. Divergent sequence means a sequence which is not convergent. Means a sequence which is not convergent is called a divergent sequence. For example, let xn is equal to n square for n belongs to n, then the sequence of real number xn is 1 plus 4, 9, 16, 25 and so on. See, this is not convergent sequence of real number, so it is divergent. Let xn is equal to minus n for all n belongs to n, then the sequence xn is equal to minus 1, minus 2, minus 3, minus 4 and so on. You can note that this is also not a convergent sequence, means it is divergent. Next example, let xn is equal to minus 1 raised to n plus 1 for all n belongs to n. Then sequence xn is a sequence whose first term is 1, second minus 1, 1 minus 1, 1 minus 1, and so on. And you can see that this is also not a convergent sequence, means it is divergent. Note that let xn be a divergent sequence of real numbers. Then there will be three types of divergent sequences. First type, xn diverges to infinity. That means limit n tends to infinity of xn is equal to infinity. Xn diverges to infinity if for every real number m there exists a natural number n node such that xn is greater than m for all n greater equal n node. Means if we take any real number m, then there must be a natural number n node such that for n greater equal n node, each term of the sequence xn greater than m. Means terms of the sequence xn are increasing and tends to infinity. For example, xn is equal to n square for n belongs to n. Then the sequence xn is equal to 1, 4, 9, 16, 25. See, in this example, if we take m as any real number, then we'll get a natural number n naught such that for n greater equal n naught, the terms of the sequence greater equal that real number m. So this is the sequence diverges to infinity. Second type, xn diverges to minus infinity. That means limit n tends to infinity of xn is equal to minus infinity. In sequence xn diverges to minus infinity if for every real number m there exists a natural number n node such that for all n greater equal n node, xn is less than m. That means by taking any real number m, there exists a natural number n naught such that for n greater equal n naught, the terms of the sequence less than that real number. Means here observe that the terms of the sequence tends to minus infinity. For example, let xn is equal to suppose minus n square for n belongs to n. Then the sequence xn is equal to -1, -4, -9, -16, and so on. Here you can see that the terms of the sequence tends towards minus infinity. And third type of divergent sequence, we say that the sequence xn is oscillate, or you can say oscillatory. If sequence xn is sequence xn neither diverges to infinity nor diverges to minus infinity, but it is divergent. For example, means xn neither diverges to infinity nor diverges to minus infinity, but it is divergent. For example, let xn is equal to -1 raised to n plus 1 for n belongs to n. Then the sequence xn is 1 minus 1 1 minus 1 1 minus 1 and so on. Here you can say that the terms of the sequence are finite. They are not tending to infinity or minus infinity, but it is not convergent. Means the terms of the sequence are oscillating 1 minus 1 1 minus 1. So this is called as, this type of sequence is called as oscillatory sequence. Let's see another example. Let xn is equal to -1 raised to n plus 1 into n for n belongs to n. Then xn is 1 minus 2 3 minus 4 5 minus 6 and so on. You can see that the terms of sequence are not, all terms of the sequence not tends to infinity or not tending to minus infinity. They are oscillating. Therefore, this is oscillatory sequence. Okay. I'm stopping the video. In the next video, we'll see the we will see the topic bounded sequences of real numbers. Thanks for watching the video.